My name is Kenji Yasunaga. This talk is about replacing probability distributions in security games. As a motivating example, let's consider a security game for public key encryption. There are two parties, an adversary and a challenger. First, the challenger generates a pair of keys, and the public key is sent to the adversary. Then the adversary returns two messages, M0 and M1. The challenger generates a random bit B and compute a ciphertext of message MB. Then the ciphertext is sent to the adversary, and adversary tries to guess which of the two messages was encrypted. We say the scheme is secure if the probability of correctly guessing the bit B is close to 1/2. In this game, we use several probability distributions. First, an encryption algorithm may use random bits to generate a ciphertext. It is well known that randomness in encryption is necessary to achieve the security against chosen plaintext attacks. Next, the key generation algorithm needs to use randomness to generate keys because the secret key should be unpredictable by the adversary. We prove the security by assuming that we have a complete knowledge about these distributions. However, in practice, we need to use approximated version of the distributions. So the question we want to ask is, what closeness do we need for distributions to preserve the security level? In cryptography, we usually use the statistical distance, also known as the total variation distance, for measuring the closeness of distributions. This is a definition of statistical distance. It is defined as the sum of the differences between probabilities of P and Q. The red figure represents the probabilities of ideal distribution Q and the real distribution P. The area of the green part is the quantity of the statistical distance. Using the statistical distance, we can make a straightforward analysis of the real game security. Suppose that the adversary wins the ideal security game GQ with probability epsilon, where Q is an ideal distribution employed in the game. Also suppose that the statistical distance between P and Q is at most delta. Then we can conclude that adversary can win the real game GP with probability at most epsilon plus delta, where GP is a game in which the ideal distribution is replaced with a real distribution P. Therefore, if we want to preserve 80-bit security, namely, if epsilon P should be about 2 to the minus 80, then it is sufficient to achieve the closeness of 2 to the minus 80. This is a typical security analysis using statistical distance. The question we want to ask in this work is there any other useful closeness measure for distributions? The answer is yes. It's Hellinger distance. In this work, we show that in Hellinger distance, the closeness of 2 to the minus 40 is sufficient for preserving 80-bit security. In the case of statistical distance, the closeness of 2 to the minus 80 is required. This result can be applied to both search and decision games. In particular, to apply our result to decision games, we use the unified framework proposed by Micciancio and Walter in 2018. The first result does not imply that Hellinger distance is more useful than statistical distance, because it is not clear if the closeness of 2 to the minus 40 in Hellinger distance is easier than 2 to the minus 80 in the statistical distance. So as a second result, we show that the leftover hash lemma holds for Hellinger distance. Interestingly, we can obtain the same parameters as for the case of the statistical distance. By combining the two results, we can conclude that the entropy loss of the leftover hash lemma can be reduced by half using the Hellinger distance-based analysis. We move on to the technical details of our work. This is the definition of the Hellinger distance. It may not be intuitive, but we can understand the quantity geometrically. This is a case that distributions takes two values, 0 and 1. Each distribution can be mapped to some points on the unit sphere. The Hellinger distance can be understood as the Euclidean distance between 2 points divided by the square root of 2. There are several useful properties of Hellinger distance. First, it takes values between 0 and 1. Second, the Hellinger distance gives upper and lower bound on the statistical distance. The third one is the most important in our work. Consider L-wise product distributions, PL and QL. Then the Hellinger distance between PL and QL is bounded above by the square root of L times the Hellinger distance between P and Q. By the relation to the statistical distance, we can show that the statistical distance between PL and QL is bounded above by the square root of 2L times the Hellinger distance between P and Q. If we use only the statistical distance, the bound is L times the statistical distance between P and Q. This difference is the key to our results. Let's describe one formal segment of our results. Let GQ be a security game in which we employ an ideal distribution Q. The winning probability of adversary A in GQ is denoted by epsilon Q. In the case of such game, epsilon Q should be close to 0. Say it should be at most 2 to the minus K. In the case of decision game, epsilon Q should be close to 1/2. Let GP be the security game in which a real distribution P is employed instead of Q. The winning probability of the adversary in game GP is epsilon P. Then, as a result for such games, we show that if epsilon Q is at most 2 to the minus K, and the Hellinger distance between P and Q is at most 2 to the minus K over 2, then epsilon P is at most 2 to the minus K. We will describe a proof overview of the theorem. We consider L independent place of game GQ, which is denoted by GQL. Let epsilon QL be the probability that adversary A wins at least one game out of L games. By definition, this value is equal to 1 minus 1 minus epsilon q to the L, which is approximately equal to L epsilon q or small epsilon q. We define GPL and epsilon PL similarly. Then the difference of two probabilities, epsilon PL and epsilon QL, can be bounded above by the statistical distance between PL and QL, which is by its total data processing inequality. Also, by the property of the Hellinger distance, this value is bounded above by the square root of 2L times the Hellinger distance between P and Q. Now we choose L to be 1 over epsilon P. Then the left-hand side is approximately equal to L epsilon P minus L epsilon Q, which is equal to 1 minus epsilon Q over epsilon P. By assumption, epsilon Q is at most 2 to the minus K. So this equation is at least 1 minus 1 over epsilon P to the K. The right-hand side is bounded above by the square root of 2 over epsilon P to the K. To keep the inequality hold, epsilon P cannot be large and should be close to 2 to the minus K. This is a proof overview. To discuss the case of decision games, we use the bit security framework of Micciancio and Walter. They introduced a framework for bit security that captured such as decision games in a unified way. A feature of their framework is that the adversary is allowed to output the failure symbol but. They defined the advantage of the adversary using the Shannon entropy and mutual information. Here we do not give a detailed definition. They proved that the advantage can be approximated by the following values. Interestingly, they have different forms depending on whether games are such type or decision type. In such games, the advantage is equal to alpha A times beta A, where alpha A is the probability that A outputs a value other than but, and beta A is the probability that A wins the game under the condition that A outputs the value other than but. In the case of such games, this advantage is equal to the probability that A wins the game. In the case of decision games, the advantage is defined as alpha A times the square of 2 beta A minus 1. The bit security is defined as the minimum value of log base 2 of TA over the advantage of A, where TA is the line type of the adversary A. As a result, if alpha A is equal to 1, namely if adversary A does not output a failure symbol, then a decision game with winning probability at most 1 over 2 plus 2 to the minus K over 2 has K-bit security. However, we need to analyze more general adversary who may output the failure symbol. As a second result, we show that if the game GQ has K-bit security and the Hellinger distance between P and Q is at the most 2 to the minus K over 2, then the real game GP has K-bit security. The proof is similar to that of the theorem in Micciancio and Walter in 2018. They proved the result for efficient divergence delta. Hellinger distance only satisfies the relaxed version of efficient divergence, but we can prove the similar result. One example of distance measure satisfying the efficient divergence is the max log distance introduced by Micciancio and Walter in 2017. Thus, the Hellinger distance and the max log distance gives the same effect in replacing distributions in security games. So we want to know the relations between the Hellinger distance and the max log distance. For this problem, we show that the Hellinger distance gives a tighter estimation than the max log distance in general. First, we show that Hellinger distance is bounded above by the max log distance as long as the max log distance is at most 0.41. Also, we give a concrete example of distributions P and Q such that the max log distance is equal to 0.6, but its Hellinger distance is exponentially small. Therefore, we propose to use the Hellinger distance and max log distance to estimate the closeness of distributions in security games. Next, we briefly describe the result of the leftover hash lemma. This is the famous leftover hash lemma, which states that a universal family of hash functions gives a k-epsilon strong extractor, where k-epsilon extractor means that given a randomness source X with mean entropy K, the extracted distribution is close to uniform within epsilon in statistical distance. The parameter n is the output length of the extractor, and the value k minus n is called the entropy loss. We show that the same universal hash functions gives a k epsilon strong Hellinger extractor with the same entropy loss, where the closeness is measured in Hellinger distance. We give a proof overview. The proof of the leftover hash lemma consists of two parts. First, we show that a universal family of hash functions gives a randomness source with low collision probability. Next, we show that a low collision probability source is close to uniform in statistical distance. In this work, we show that a low collision probability source is also close to uniform in Hellinger distance. To prove this, we use a technical lemma given by Chang and Badan in 2008. We compare our result with the related work of Barak et al. They show that the entropy loss of the leftover lemma can be reduced by half for a restricted class of primitives, including all source primitives and stateless encryption and weak pseudorandom functions. In this work, we show that the same effect can be obtained for all primitives if we use the bit security framework of Micciancio and Walter. In the analysis, we use the Hellinger distance. We conclude our talk. We showed that the Hellinger distance is useful for measuring the closeness of distributions in security games. we show that the closeness of 2 to the minus k over 2 is sufficient to preserve the k-bit security. And we show that the leftover hash lemma holds with the same parameter as for the case of the statistical distance. Interesting future work is to explore another example such that the closeness in the Hellinger distance within 2 to the minus k over 2 is easier than the closeness in the statistical distance within 2 to the minus k. In this work, we show that it holds for the leftover hash lemma. Another future work is to explore other useful closeness measure than the Hellinger distance. That's all of our talk. Thank you.